I want to begin with a question that I have been turning over in my mind for most of my adult life, and I suspect you have turned it over in yours too, even if you haven't quite put it in those words. The question is simply this: where is everybody? That question was asked rather famously by my old colleague Enrico Fermi over lunch at Los Alamos in 1950. He asked it in his characteristically blunt way, and nobody at that table had a satisfying answer. I still don't have one. But I have come to believe that the most important part of the question isn't whether there is anybody out there. I think there almost certainly is, but rather why the universe appears to conspire so thoroughly against anyone visiting anyone else. And the answer, I will argue, is time, not the absence of intelligence, not the absence of motivation, time. The universe is not just large in space, it is staggeringly, almost maliciously, large in time. And those two things together, the spatial distance between the stars and the temporal penalties imposed by the laws of physics, create a situation which I think we can fairly describe as a kind of cosmic imprisonment. Alien civilizations, if they exist, are not simply far away. In a very real and very physical sense, they may be stuck in time in ways that make the idea of interstellar contact not merely difficult, but almost paradoxical. Let me explain what I mean by that, and I will try to be concrete, because I think the numbers are where the truth lives. The nearest star to our Sun is Proxima Centauri. It sits about 4¼ light years away. That sounds almost manageable. 4 light years. We have sent spacecraft to the edge of our solar system. Voyager 1 has left the heliosphere. Surely we could, with sufficient ambition, reach a star 4 light years distant. Now, Voyager 1 is moving at roughly 17 kilometers per second. That is fast by any human standard. At that speed, Voyager 1 would reach Proxima Centauri in approximately 73,000 years. 73,000 years. Human civilization as we understand it. Agriculture, writing, cities is perhaps 10,000 years old. We would need to sustain a technological project 7 times longer than the entire span of recorded human history, just to reach the nearest star at our current best speed. And Proxima Centauri is not by any measure an interesting destination. It is a dim red dwarf with a planet of questionable hospitability. So what would it take to do better? This is where physics becomes both your greatest ally and your most unforgiving adversary. If you want to cross interstellar distances in any reasonable time, and by reasonable I mean within a human lifetime, you must travel at a significant fraction of the speed of light. There is no way around this. You cannot negotiate with the distances involved. The galaxy is 100,000 light-years across. Even the nearest stars of genuine interest, the ones orbiting sun-like stars in habitable zones, are tens or hundreds of light-years distant. You must go fast. Very fast. Now, the moment you begin thinking seriously about traveling at a significant fraction of the speed of light, you immediately run into something that I find both intellectually beautiful and practically catastrophic. You run into Einstein. Einstein's special theory of relativity, published in 1905, tells us something quite extraordinary about the nature of time itself. Time is not a fixed universal backdrop against which events unfold. Time is a dimension of space-time, and it behaves differently depending on how fast you are moving. Specifically, the faster you move relative to another observer, the more slowly time passes for you as seen from that observer's frame of reference. This is not a philosophical abstraction. It has been measured. It is real. We see it in the decay rates of unstable particles in accelerators. We correct for it in the GPS satellites orbiting above us. It is as experimentally established as any fact in physics, and this means something rather remarkable for anyone contemplating interstellar travel. Imagine a civilization that has somehow solved the engineering problems we haven't. They have built a spacecraft capable of reaching, say, 90% of the speed of light. At that speed, the effects of time dilation become dramatic. For the crew aboard that ship, time would pass at less than half the rate it passes for observers at rest. A journey that takes 22 years by the clocks of those left behind on the home planet would feel to the crew like only about 10 years. At even higher fractions of the speed of light, the disparity becomes extraordinary. At 99.5% of the speed of light, a crew could traverse a distance of over 100 light-years, while aging only a single year. This sounds, at first glance, like good news, and in a narrow sense it is. It means that, in principle, the crew of a relativistic starship could cross the galaxy within a human lifetime. They would be dead long before they arrived if the galaxy is their destination, but the numbers begin to seem less hopeless. But here is where the situation becomes genuinely strange, and where the word stuck becomes appropriate, because while the crew is experiencing 1 year of subjective time, the rest of the universe is not waiting for them. The rest of the universe is aging at its normal rate. 100 years are passing at home. Civilizations are rising and falling. The people who said goodbye at the launch pad are long dead. The society that built the spacecraft may no longer exist. The language spoken when you departed may be as remote and foreign to your descendants as ancient Sumerian is to us. An interstellar traveler is, in a very real sense, a time traveler, but only in one direction and without any mechanism for return. They arrive not only at a distant place, but in a distant time, cut off from everything they knew by a gulf that is not merely spatial but temporal. Now, I want you to sit with that for a moment, because I think it fundamentally changes how we should think about the question Fermi was asking. When we ask where all the alien civilizations are, we are implicitly assuming that the universe operates something like a world where a ship can depart, deliver its cargo, and return home in time for supper. We picture contact between civilizations the way we picture contact between nations on Earth. You send an emissary, they arrive, conversations happen, understanding is exchanged, but the physics of the universe we actually inhabit does not work that way. Consider what it would mean for a civilization to mount a genuine interstellar expedition. They must first solve the energy problem, which I will come to in a moment. But suppose they solve it, they build their ship, it departs at a relativistic fraction of the speed of light. The crew ages slowly while the universe ages quickly. They arrive at their destination star system, perhaps 100 light years away, 200 years later in cosmic time, though perhaps only a decade has passed for the crew. What do they find? They have no way to know. Any signal sent home takes 100 years to arrive. Any reply takes another 100 years to return. The expedition is, for all practical purposes, irrevocably severed from the civilization that launched it. This is not merely a communications inconvenience. It is a civilizational rupture. The society that built the ship is 200 years older, transformed beyond recognition. The expedition has been funded, motivated, and directed by a civilization that no longer exists in its original form. The crew arrives as strangers, not merely to a foreign star, but to a foreign time. And this is why I think the word stuck captures something real. Not stuck in space. With sufficient energy, you can traverse space, but stuck in time in a way that makes meaningful, reciprocal contact between interstellar civilizations almost incomprehensibly difficult. Any civilization that sends expeditions across the galaxy is sending them into its own future, and the future is unknown to everyone. But let me now address the energy problem, because it is in many ways even more fundamental, and it is where the physics becomes almost merciless. To accelerate a spacecraft to a significant fraction of the speed of light requires energy on a scale that dwarfs anything in human experience. I have spent a good part of my career thinking about unconventional propulsion, most notably through a project called Orion in the late 1950s and early 1960s. Which proposed using the detonations of nuclear devices to push a very large spacecraft to high velocities. It was an extraordinary idea. Ted Taylor and I thought it was genuinely achievable, and the numbers were not dishonest. An Orion-type vessel using nuclear pulse propulsion could potentially reach perhaps a few percent of the speed of light, perhaps 3, 4, 5%. That would mean a journey to Proxima Centauri in roughly a century. Heroic, but not absurd. But here is the difficulty. Even a few percent of the speed of light is not enough to make time dilation a meaningful advantage. At 5% of light speed, the time dilation effect is almost negligible. A 100-year journey is a 100-year journey. And to get to the speeds where relativistic time dilation becomes dramatic, 90, 95, 99% of light speed, the energy requirements become nearly incomprehensible. The reason for this is something called the rocket equation, which any engineer working in space will tell you is a deeply unhappy piece of mathematics. As you try to accelerate a spacecraft, you must carry the fuel for that acceleration, which adds mass, which requires more fuel to accelerate, which adds more mass. The relationship between the mass of the fuel and the final speed of the spacecraft is exponential. As you approach the speed of light, the mass of fuel required grows without bound, approaching infinity, This is not a practical limitation that cleverness can overcome. It is a mathematical reality imposed by the structure of the universe itself. I said that chemical fuels are hopeless for interstellar travel, and I meant it. Even nuclear fuels, while orders of magnitude better, face the same fundamental problem at relativistic speeds. The most optimistic proposals I have seen, antimatter drives, fusion ramjets, scooping up interstellar hydrogen, either rely on technologies we cannot yet produce at scale, or encounter physical obstacles that are deeply difficult. The ramjet, for instance, proposed by Robert Bussard in 1960, was an elegant idea. Collect hydrogen from the interstellar medium and burn it as you go without carrying fuel. A beautiful thought, but the interstellar medium is far more tenuous than early estimates suggested, and the drag on the magnetic scoop may be prohibitive. None of this means interstellar travel is impossible in principle. I want to be careful here, because in science it is better to be wrong than to be vague, and it would be vague and probably wrong to declare something impossible simply because it is very hard. But it does mean that the energy requirements for relativistic interstellar travel are so severe that only a civilization commanding truly extraordinary resources could contemplate it. A civilization that has harnessed the entire output of its star, what we call a Type II civilization in Nikolai Kardashev's classification, might plausibly accomplish it. A civilization like ours, which has harnessed a small fraction of a single planet's resources, cannot even begin. And here is something worth thinking about. Our civilization has existed in something like its technological form for perhaps 200 years. The universe is 13.8 billion years old. The sun is 4.5 billion years old. If other civilizations exist around older stars, some of them may have had billions of years to develop. A civilization that is 1 billion years more advanced than us is as far beyond our comprehension as we are beyond the comprehension of a bacterium. Surely, one might say, such a civilization could cross the galaxy in a weekend. Perhaps, but I would offer a more cautious thought. The laws of physics are not impressed by civilizational age. The speed of light does not negotiate. The rocket equation does not make exceptions for ancient wisdom. Even a civilization 1 billion years more advanced than ours must still obey the same relativistic constraints. They may have found solutions we cannot imagine, but they have not repealed the laws, and the temporal dislocation caused by near-light-speed travel, arriving centuries or millennia after your departure, is not a problem that advanced technology solves. It is a problem that advanced technology makes more acute, because the more complex and interconnected your civilization, the more catastrophic the disconnection of your expeditions. I want to turn now to something that I think is underappreciated in discussions of this sort, and that is the problem of civilizational timescales. When we ask whether alien civilizations are out there, we tend to implicitly picture them as permanent fixtures. We imagine a civilization on some distant world that has been there for 1 million years and will be there for another 1 million years, waiting patiently for us to develop the technology to find them. But civilizations, as far as we can observe, are fragile. They are biological, cultural, and technological constructions, and constructions do not last forever. Our own civilization is perhaps 200 years old in its technological form. We do not know if it will last another 200. We have built weapons capable of destroying it, climate systems we are stressing in ways we don't fully understand, and social tensions that are, to put it charitably, unresolved. I am not a prophet of doom. I am by temperament an optimist, but I think it is important to be honest about the uncertainty. If the average lifetime of a technological civilization is, say, 10,000 years, which would be an impressive achievement by our standards, and if technological civilizations arise at the rate suggested by the Drake equation, then at any given moment the galaxy contains a certain number of them, but they are not all contemporaneous in any meaningful sense. A civilization that arose and flourished and then vanished 500 million years ago left no messages we could detect, no artifacts we could find, no descendants we could meet. The universe is very old, and civilizations that existed in what we might call the Cambrian of galactic history are as remote from us in time as the Cambrian is from us in biological history. They are not absent from the universe, they are absent from now. This, I think, is a deeply underappreciated aspect of the Fermi question. We are not merely searching in space, we are searching in time. and the overlap between our temporal window of technological existence and the temporal windows of other civilizations may be extraordinarily small, even if those other civilizations are numerous in an absolute sense. The chance of two civilizations overlapping in time and space simultaneously and being close enough for any kind of contact depends on parameters we do not know, but which may be severely unfavorable. I have thought over the years about what a truly advanced civilization might actually choose to do with its capabilities, and I confess my speculations have become increasingly unconventional. A civilization that has mastered relativistic travel can, in principle, use time dilation as a resource. If you move at very high velocities or orbit very near a massive object, a neutron star, say, or the supermassive black hole at the galactic center, time passes more slowly for you relative to the rest of the universe. You can, in effect, fast forward through the external universe. While 100 years pass on distant worlds, you age only a few years. This is not time travel in the science fiction sense. You cannot go backwards, but you can choose to be a slow traveler through time, experiencing far less of it than the universe at large. And I have sometimes wondered whether this might be the fate of truly advanced civilizations, not spreading across the galaxy in the way we imagine, but retreating into time-dilated enclaves, experiencing the universe at their own chosen pace, watching eons pass outside while they tick along at their own serene rate. They would be present in some sense, but they would be profoundly inaccessible to anyone moving at normal cosmic time. There is also the question of what interstellar travel is actually for. We tend to assume that any civilization with the capability would expand, colonize, spread. This is a very human assumption rooted in our own history of exploration and migration, but it is not obviously correct. A civilization that is sufficiently advanced may have created such richness within its own star system, virtual worlds of unlimited complexity, forms of experience we cannot imagine, biological and cultural achievements of extraordinary depth, that venturing across the cold void to plant a flag on a distant rock holds no particular appeal. I do not say this is likely, I say it is possible. And possibility in matters of this kind is what we should be reasoning about honestly. The physicist Enrico Fermi's question has often been interpreted as evidence that we are alone. I do not read it that way. Fermi was pointing to a genuine mystery, not announcing a solution. The silence of the cosmos, such as it is, and our search has been far from complete, is consistent with many possibilities. It is consistent with the hypothesis that technological civilizations are rare. It is consistent with the hypothesis that they are common but short-lived. It is consistent with the hypothesis that they are common and long-lived but choose not to communicate in ways we recognize. And it is consistent, I think, most interestingly with the hypothesis that the physical structure of the universe, the speed of light, the vast distances, the cruel mathematics of the rocket equation, and the dislocating effects of relativistic time conspires to make meaningful contact so difficult that even a galaxy full of civilizations would appear from any given vantage point to be essentially empty. The universe is not empty of life, I suspect. It is empty of contact, and the reason is time. I want to close with a reflection that I find both sobering and strangely hopeful. We know beyond any reasonable doubt that the atoms in our bodies were forged in the interiors of stars that died before the sun was born. Carbon, oxygen, iron, the stuff of life is the ash of stellar nuclear furnaces. We are, in a very literal and not merely poetic sense, made of the same material as every other possible living thing in the universe. Any alien creature anywhere in the cosmos shares this ancestry with us. We are, all of us, children of the same ancient stars. That is a kind of kinship that does not require contact to be real. We are already connected by physics and by chemistry to everything that lives or has ever lived under any star. The distances are vast. The time barriers are severe. The chances of meeting may be extraordinarily small, but the connection is there, written in the periodic table, confirmed in every carbon atom of every creature that has ever breathed. Perhaps that is enough to be going on with. I am a philosophical optimist. I believe the universe is generous. I believe that life, given enough time and enough chemistry, finds a way. And I believe that the question Fermi asked at that lunch table in 1950 is still the most interesting question a physicist can ask. not because we have answered it, but because in honestly confronting it with real physics, real numbers, and real humility about what we do not know, we learn something profound about the nature of the universe we inhabit. The aliens, if they are out there, are stuck in time just as we are, separated from us not merely by light years, but by the irreversible asymmetric arrow of cosmic time. We are all prisoners of the same physics, and perhaps that too is a form of companionship. Thank you